In this video we're going to do a couple of things. We're going to start by taking the shader specific code that's in our main game class here. So these variables here and this code here, and then whatever we find that we're referencing the shader directly in our code, and we're going to move that into a specific shader class, and then we're going to move things around until we have the same functionality as we had before, but with all the shader specific code separated into the shader class. After we get that working, we're going to add functionality to the shader itself, to the shader text itself, and add whatever variables and functionality we need in our program in order for that shader stuff to run properly. But to begin with, let's just go in here. I've refactored the packages a bit here, but otherwise they should be unchanged since the last video. So we can just start by looking at what this program does. Just moving the camera around. We're lighting this from the point of view of the camera, and we have a separate viewport there, and so on and so forth. So for now, let's just leave this as it is. Go in here and add a new class. So this class we'll simply call shader. You can call it shader 3D if you're going to have separate shaders for two-dimensional overlays and stuff, but look at that later on. For now, let's just call this shader and get onto here. I think we'll just add a constructor, and we'll see later on if we're going to need any variables here other than this. But let's just go here, and we have our shader specific variables here. We can start by just deleting this. We don't need this anymore since we have the matrix functionality elsewhere. Okay, so the IDs of the shaders and programs and the location variables. We'll just take those out of here and put them into the shader. And then to begin with, we'll go into the create function. So this is part of the callback functionalities, but everything below that and up to here, use program, we'll also just remove that entirely and put it into the shader constructor. So the shader is happy with this for now, but the game class definitely isn't. So we'll go through the errors that are happening here. Okay, here we're trying to talk directly to the shader using this color location. So instead of this, we're going to want to go into the shader and say this code here should be in the shader, but we're going to need a function in the shader to talk to that. So let's go in here and say, let's make a function that's called public void set color, and here we can just take 4 floating point values, or we could actually make, let's just take 4 floating point values for now. Float red, green, blue, and float alpha. We could also make a small helper class for the color that we send in there if at any point it feels better in the rest of your program to have the colors floating around not as individual floating points or not as individual numbers, but as a class. Definitely go ahead and do that. So we're going to move this code in there. Let's just start by actually going in here and adding one shader program. Shader here. So, and we'll simply, in the create function where we used to put the shader code, just call shader equals new if you want your shader to have functionality where it changes things around or loads different shaders, you can new it first and then call load shader, or we can do all sorts of things. For now, the constructor just builds the shader. The shader itself has the link to the shader code. Maybe a more generic type of shader would have variables that it takes in with the shader code, so you can make different shaders from this. For now, let's just have this fixed. This particular shader has particular variables that we need to be able to talk to. So let's just stick to that for now. So shader equals new shader, and now instead of this call here, we're going to say shader dot set color. I'm just going to use the same numbers here, and this is going to go into the shader. So here we have set color, and now we have a scope where color location is known, and we just have R, G, B, A, red, green, blue, alpha. Fine. Okay, then let's just look at the rest of the errors. So okay, here we have a reference to the position location and the normal location in box graphic. So if you look at this function, you can see whether this is important to have here. The reason for this is because when we draw, we actually use the pointers here. If we were to do it another way around, we'd somehow have to send the draw function through the shader or grab that every time. So let's allow this for now, even if it means that there's shader specific values here. We can refactor this later on, but for now what we need then is public int get vertex pointer is what we call it, right? Vertex pointer and normal pointer. Let's just call it the same. Get vertex pointer. Return position location. And another function for get normal pointer, returning the normal location. Okay, so then we can fix this simply by saying shader dot vertex pointer and shader dot get normal pointer, and we can overwrite this in the rest of them. Why am I getting an error up there? Save. And let's make sure that inside the shader we're doing vertex pointer. This, yes. Okay, so box graphic. Okay, so the next error here is the model matrix location. So I kind of want to do this the other way around and say now we're not going to actually access the model matrix location and send it into the matrix, but instead we're going to change the matrix class a little bit. You can do the same thing as we did here, just make functions on the shader that give us these locations and use those. But instead I'm going to change this around a little bit and go into here, set shader matrix, and instead I'm going to build a function here called public buffer get matrix. And then we can take this out. Now we'll comment it out, but we should be able to simply throw that away in the end. And so instead of this, we're going to go into the shader and we're going to say, let's build a function here. It's called public void set model matrix. And that takes a float buffer matrix. So import. Okay, so the code we have here, we're now going to take that and put it into the shader instead. So the shader will know these things. Since this is a function that's only putting data into the shader, I'd like to just have that in the shader class. It's different from what's happening in the graphic classes, in that they're calling draw and there's other functionality and other things they're referencing that are their own things. So we have to send data one way or the other. Here, however, we can just say no one needs to know about these shader specific things except the shader. So we'll just send the matrix into the shader because that's the normal way for the data to flow. We're building the matrix in one place and then sending it down into the shader. Okay, so shader matrix pointer is not what we're using here because we have model matrix location here already. We don't need that. So this is set model matrix, and let's just make two more functions here. Set view matrix and set projection matrix. And use these locations here. We'll use that soon enough. So what we now do here is instead of this, go and we say shader.set model matrix, main.get matrix. Okay. Again, our camera should not have to take these variables here. So we'll go in here and say we're not going to keep track of the view matrix pointer or the projection matrix pointer inside the camera class anymore. Instead, we are going to make a couple of functions here. Float buffer get matrix and projection matrix. And we can take this, say this gets the projection matrix, turn matrix buffer, and this part here sends us the view matrix. We need this, and we are going to need the return. Otherwise this should be fine, and this is now happening inside the shader instead. Okay, so now we can get the projection matrix, and we still know if it's orthographic it's this, otherwise it's this. We end up receiving the matrix buffer, and then we don't need to build the camera with this. We don't need to build the camera with this, otherwise the camera class works the same, except when we call cam set shader matrices. Instead we're going to have to go and say shader set view matrix cam get view matrix. Same for projection. doesn't get to set its own shader matrices anymore. And we can take the same thing here, except put orthocam in there instead. No, not there. That was still supposed to be shader. Orthocam goes here. Put that on. Okay, yeah, obviously we still have errors, but these are fixed. Next error here, we have the color location. So let's just go to where we had that. First shader.setColor. So, and then we can simply there, setting the same color. Color location again. Color location again. And finally here we have this line. So it's now shader.set model matrix. Model matrix dot matrix. So, and one more error. Same again. Let's just find, where was that earlier? Set shader matrix was somewhere here. Where do we have shader dot? Here. Shader dot set model matrix. Okay, this one was above. Okay, so now we don't have any errors. The question is though, does this simply work? Shader and all? It seems that it does. Okay, so now we have everything working and our data is flowing nicely through our program. Let's just look at the cameras we have set up. No ridiculous near planes or far planes or anything like that. Now this camera is set up here. This is fairly nice setup. Okay. Now let's just for a moment go through the shader itself here and see what all of the code now does inside the shader. So the first things here we have, we're simply reading this file into a string. So this string here holds the code, just the program text of the Vertex shader, and this string has the program text, the code for the fragment shader. We don't use that yet, but what we first do is we say OpenGL, create a shader for me. It's supposed to be a Vertex shader, and give me an ID for that shader. So from now on, I know how to identify the shader that I'm using. This means that I can use several different shaders. I'll have IDs for each one of them, and I can tell OpenGL to compile and use different shaders at different times. So I get the Vertex shader ID, I get the fragment shader ID, but for now these are just empty programs. OpenGL doesn't have any program text for that. That happens when I call GL shader source, and I say OpenGL, for this Vertex shader ID that you gave me, here's source code that you should use to compile that shader. Same for the fragment shader. And finally, I say OpenGL, now compile the shader that has this ID. I've linked this program code to it, coming from this text string here. Now compile it, and at this point we can get errors, and there are functions on OpenGL where we can ask OpenGL what exactly the errors are. gdx.gl. I think there's a get error here. This function here will give us an integer for the error we're looking at, and then you can search for that, what the error codes mean. There's shader info log, will give you a more detailed error if you're getting errors here. So you can check if there are actually errors happening when you're compiling the shader, and if there are errors, you can use the shader log to see what that is. In order to use this, if you're getting errors on your shader, it's simplest just to kind of Google what different errors mean and how you can use the shader log to identify what's wrong exactly. So for now, let's just imagine that we're not getting any errors. Let's add the error messages later on, just to keep this simple for now. So at this point, we've compiled both the shaders, and we do the same thing as when we asked OpenGL to create a shader for us. We tell OpenGL to create a program. And the program is basically a combined or a combination of the compiled Vertex Shader and the compiled fragment shader. So we just get an ID for a program, there's nothing in it anymore. Then we attach these two shaders to this program using this rendering program ID, and finally we do link program with the rendering program ID. So we've compiled each shader, we add each compiled shader to this program, and we link the program. And if everything adds up, if all the variables fit between the shaders and there's nothing wrong in how they compile, this should simply now be set up so that that's the shader that we use. Alright, so all of this is just taking the shader text and linking that together. Parts of what needs to be linked here, if we go into Assets, Shaders, and look at the Vertex Shader, for instance. Look at the Vertex Shader and look at the Fragment Shader. Here, for instance, we have this varying V-color, and that needs to fit to a varying V-color in the fragment shader, because varying means that this is a variable that we allow to flow between the shaders. That's the only thing we actually use in this super simple fragment shader. Then we have these variables here. Then we have these attributes, which are the normal lists and the position lists, or the vertex lists that we send in. We just get one at a time into the shader out of the list, but we can set these attributes up as lists. These are just variables that we can set. And so inside the shader code, the next things that happen here is we're simply saying we have these integer variables and we want to get IDs from OpenGL for the locations of different variables inside the shader. So I want to be able to access this attribute a position. So please get this attribute location from this rendering program that's named this and send it to me. An important thing to note is that if you want to use something like a matrix in both the vertex shader and the fragment shader, you can simply use the same name in both of them, or it doesn't matter in which of the shaders a certain name is used. If you're going to be using certain things on either side, you just have to make sure that the names don't conflict. If you have the same name for things that are supposed to be doing different things, that'll be a conflict. Because in the end, when we access this, we're accessing all of the variables here in both shaders together as one set of variables. The varying parts, we don't access them from outside. Instead, they are something that we set in the vertex shader and then use again in the fragment shader. But all these uniforms, they are simply variables that we access from outside. So position and normal, they're both attributes, and we'll enable them to be sent in as arrays. So enable vertex attribute array for position location and for normal location. Then we get model matrix location, view matrix, and projection matrix, and then the color. And that's all we have in this simple shader that we're using now. So the name uColor is in here. That's something that we send in. And we tell OpenGL, in this rendering program, there's a variable called u_color. I want the ID for that. I'm going to store it myself in this variable here, color location. And then whenever I want to set the color, I call GL uniform 4f with this color location. 4f simply means that I'm filling a vector which has 4 floating point numbers. If I simply set up a float in here and say I'm going to set up a uniform float u data, then in my vertex, in my shader here, I'd have to get some location for that called data location, and then there are different, so GDX, GL, GL uniform. So one float would be what I would be using there. One float sent in from vector, doesn't matter. Then I have one float sent in from a vector where I have an offset. I think we just use this one for one float. Then we have a vector with 2 floats using 2 numbers. We have a vector with 3 floats, a vector with 4 floats, which was we're using here. We send in the location, which is the pointer, and then we send in these 4 values. And these 4 values will be sent into, since this is a vector with 4 values, it'll simply be put in those values. And finally, we have matrices. Matrix 2, which means a 2 by 2 matrix, 3 by 3 matrix, 4 by 4 matrix, which is what we're using. When we set here, uniform matrix 4 means 4 by 4 matrix, and we're sending it in as a floating point vector. And in GDX, that means we're sending it in as a float buffer. We're sending it in as a buffer rather than just 16 values. But I believe there's also a version of this. No, we can send in a float array here though instead of the float buffer, if we feel better using that. Anyway, we've set this up with the float buffers now, so let's stick to that. So this is what happens in the code. We're getting these identifications for different variables in the code, and then we're using them. We're saying OpenGL now, anytime this is called here, the variable at this position, which is the u_color variable, should have these 4 values set into it. And then the next time the shader is called, those are the values that will be used when the main program in the shader is run. And same for the matrices. We send this matrix in, and these are the values that will be used the next time in whatever model matrix lock points to, which is u_model matrix, which is here, u_model matrix, and is used here in a matrix multiplication. So that's all we have here for now inside the shader. And the shader is now working nicely with its original functionality. And obviously all the manipulation of the matrices themselves and that stuff is unchanged. It has nothing to do with the shader except when we actually send the matrix data into the shader. Besides that, we just program ourselves all the data and matrix and geometry manipulation. So that's nice. So the next thing we do is simply to start changing the shader itself. So for now, we're going to work in the Vertex Shader, and we're going to do everything we do kind of in order for it to affect each vertex, and we end up with a color when we're done with the main function here, and that color will simply be interpolated onto different pixels, and we simply use whatever color we get here. It's not the same color. This is one color for each vertex, and then that's kind of made into a gradient over all of the pixels, kind of a weighted average between the vertices of the polygon that we're drawing, the colors of the vertices, depending on its position. And for each pixel, we get one weighted average between the varying variables. And in this case, the only varying variable is color. So we're doing a vertex lighting and then we simply get a gradient between those colors onto the pixels. So the fragment shader is shading the pixels themselves. So fragment shader, let's leave that simple still, but put something a little bit more interesting into our vertex shader. So fragment shader we leave simple, vertex shader we edit. So to begin with here, we have our model matrix, view matrix, and projection matrix, and we'll keep them separate. At some point we might say that if all our calculations are happening either in global coordinates or in I coordinates, we can combine either a model view matrix or a projection view matrix. But for now, let's keep them separate. It'll be a bit better optimized if we combine some of them, but since we're learning this now, let's keep them nice and separate. So what we've been doing before is we've been doing this simple calculation where we imagine we have a light in the eye, and so we do this just in eye coordinates. What we're going to do now though is we're going to take this lighting out and we're going to build a lighting in the global coordinates instead. So lighting, and we need some data for that. So to begin with, we're going to have a very simple light, but we're going to give the light a position. So we're going to need a uniform light position, and we actually only need vector 3 for that. For now at least, we might want to use the fourth coordinate to decide whether it's a position or a direction. So we can just leave it in there and just not use it to begin with. So we have the light position, we already have this position, and since we're building this up into a vector 4 position here anyway, we can just as well have this a vector 4, since we might have to use these together. So we have a light position, and what we had was simply a color, but let's go and say instead, let's call this light, no, not ambient, light diffuse. So this is going to be the diffuse part of our light. And we're just going to have a single light here now, and the shader will only handle a single light. So we're not going to make any arrays here, we're not going to make different lights. Just keep it simple now and we can add on it later. So this floating point was just something we made earlier to demonstrate something. So we're going to have a light position and we're going to have the diffuse of the light, and instead of the color itself, we're going to have a vector 4 uniform material diffuse. Like so. So we have the diffuse of the material and we have the diffuse of the light. And then we have the light position. So instead of the color, now we need ways to set all of these. So before we continue, let's just make sure that our shader actually handles this. So we're already setting color here. So let's take that out for a while. And instead say we want to be able to set material diffuse. We want to be able to set light diffuse, and once this starts growing into several different lights, we might want to change this a bit and not have a separate function for every single value that we have in there. For now, again, we're keeping this simple. Material diffuse, light diffuse, and light position. So we can either have X, Y, Z, W, or we could actually take a point in here. Let's decide that later on. So for now, we're actually going to change this as well. So we need to make sure we're not using this color location here. We'll do 3, take the original color location out because we don't have this variable in our shader anymore. And now we have light position, light diffuse, and material diffuse, all of them vector 4. Light position, light diffuse, and material diffuse. And then we need variables for that as well. So light position location, light diffuse location, and material diffuse location. Light position, light diffuse, and material diffuse. Alright, so we have this, and we need to get those positions, and we need to set them to the correct place here. And in this case we have to change this to wait. Yes, this is the position part. X, Y, Z, W, and obviously this one should be at the top, I think, just to keep it consistent with the rest. Which means that I'm going to need to switch all this around. It's still not right. Need to switch these around as well. So light, material. So light position location, light diffuse, and material diffuse. So we have these variables, we can set those, and we have them in a shader. Before we start setting them in the game itself, let's make sure we use them. What happens if you define a variable here and then don't use it in your code, or it doesn't result in anything in the code? When OpenGL compiles the shader, it'll actually skip that variable entirely, and that means that if you don't use it in the code and then you start asking for an ID for it or a location for that and start trying to use that location, OpenGL will simply result in an error and your program can crash because of that. Even though you actually have the variable here, if you're not using it, it'll simply not be compiled with the rest, and so you'll get an error when you try to access it. So make sure that anything you have in here you use, and anything you're not using should actually fully comment out, or mainly make sure that you're not trying to reference it from your code. So now let's start using these this data. So we have this lighting calculation here, where we're doing this dot product here and normalizing things and taking these positions. So let's just do the full-blown diffuse lighting here and start by saying we're going to make a floating point called Lambert, and that equals the dot product of some vectors. Okay, so we have the normal to the object itself. So that's one part of this, normal dot product, and the other part is the direction to the light. So if we're imagining that this is a light with a position, what we now need is a vector pointing to that light. So we're going to need a new vector vector here, like 4, and it's called S in the math. If you go into your slides and see these calculations, so S equals the light position minus our current position here. Another thing we have to make sure is that the positions that we use for the light are thought out to be in global coordinates. Otherwise, if we're thinking of them in local coordinates, we have to make sure that that position, when we set the light, is somewhere in our code multiplied through our current model matrix and such, but it's much more easy to just imagine the lights being in your global coordinates. And we're using them in global coordinates and we're not changing them, so make sure that you understand the distinction between that. So here we have the vector S, which equals the difference between the light position and position. So the dot product between normal and S, and then we can either normalize each of them and say normalize like this. But what happens here is that we take the length and then divide the length into all three or all four coordinates. So we don't want that. What we want instead because it's just a little bit cheaper, is to say we're going to take this dot product first and then we're going to divide it by the length of the normal divided by the length of S. No, sorry. Multiplied by the length of S, and make sure that this is inside. And this is here, like so. Okay. So here we should have our Lambert factor. And what happens with the Lambert factor now is that it basically tells us the intensity of the directions or of how the light hits the material or hits the object. Then we need to take the material itself. So now we're going to say the color equals Lambert times our material diffuse or light diffuse times U material diffuse. Needs to have a U underscore here as well. It's actually okay in this case in the OpenGL shading language to multiply two vectors together, even though that operation doesn't make sense in the classic linear algebra sense. If we use two vectors and multiply them together, they'll multiply component wise. So they'll take the first two coordinates, or the first coordinate from each one, and multiply them together, the next coordinates and multiply them together, so on and so forth, and then build a vector of equal size to the ones that we multiply together. So of course, if you have two vector 4s, the regular way to multiply them together would be to have one in a row matrix, the other in a column matrix, and they end up with a single number, which is the dot product. And multiplying vectors isn't really something that's real in actual linear algebra. When, however, we multiply matrices together, they do it in the regular linear algebra sense. And when we multiply either vector times matrix or matrix times vector, they also do it in the proper linear algebra sense. And every time we multiply a vector to the right side of a matrix, it'll be set up as a column matrix. Well, the vector will be made into a column matrix. If we multiply it to the left side, it'll be a row matrix. However, here we do this component wise, so we don't actually have to split this into the separate colors. We can just do this multiplication here, and they'll happen for all the colors at once. So we have the Lambert intensity, which is built on this vector S pointing to the light. That's where we use the light position, minus our current position of of the object itself, or of the vertex itself. Lambert takes the dot product between the normal, which is the other direction that we use. So we get this cosine of the angle between these vectors, giving us the intensity. And we take that intensity and multiply with the colors of both the object and the light. So now we have the color, and then here we end up with the position. So we're doing this inside global coordinates, and that actually means that there's no reason for us now to multiply the normal with the view matrix, because we're not using it anymore. We multiply the position with the mu matrix and then the position with the projection matrix. And as you can see, with this particular shader, we could just as easily send in one matrix called the projection matrix, which we multiply together beforehand, and that'll make everything much cheaper here. Then we have only one matrix multiplication in the shader, and the shader happens for every single vertex. Whereas we could do the matrix multiplication once instead before we send it in there, and save ourselves a lot of, so one big multiplication before, and then skip half of the matrix multiplications throughout for each vertex. So for now, we're going to leave it like this though. But we don't need to have this in here as well. So okay, now we have a shader which has these variables and actually uses them. We have a shader class that allows access to all of these same variables and doesn't use the old color variable. And now we simply need to go in here and say set color. Doesn't do anything for us. And actually setting the color here isn't really something that we need. What we might want to do though is go into the shader matrix and call each of these just to make sure we have some data in them. Or we could actually do that. Oh, it can be done here. That's the main reason, just to make sure we don't end up running the shader with no data in it. But we'll just make sure that happens in our display function. So here we have display, and in the display function, in some places we're calling set color to something new. We call that always before we draw, so we make sure we're not actually drawing anything until we've set a color. We have to do other things as well. We have to make sure that, okay, let's just put in here. So shader dot set light position. Let's just set it now to some nice arbitrary position. Let's try 0, 0, 0, 1. And we can just see in the image where exactly that is. Okay, then shader dot set light diffuse. We should start with an entirely white light, just to make sure that we'll actually see it properly. And then everywhere where we have the error, we'll change that to set material diffuse. So we're not setting color anymore as such, we're setting the diffuse value of the material. And let's see, okay, so this works, and we can see that everything is now lit, but the lighting isn't changing based on where we're at. There's obviously a light somewhere. Here I go to the other side and suddenly everything is dark, because we have a light that's in a specific location and it lights everything from the side. The distance to the light has no effect. So we can actually see, okay, we see this side is lit, this side is lit, this side is lit, suddenly it isn't. So the light is somewhere inside here. And do we end up somewhere? Okay, so the light is somewhere around here. This is more or less the 0.0. Okay, so we have the light, but in order to actually get a better feel for what's happening with the light position, So this is basically ready now. Our shader is ready with the diffuse lighting. But in order to manipulate it a little bit and see actually what's happening, we would actually like to set the light position in a more interesting way. So I always love having this angle here that I'm just changing with delta time, because taking the cosine or sine of an angle will give us values between 0 and 1, which is always something that's nice to have, especially when working with colors and when working with positions. So now we're going to take the light position and we're going to set it a little bit higher. Let's set it up to like 4 on the Y. Let's go ahead and do something like float s equals math dot sine of our angle, and as always times math dot pi divided by 180 degrees. And then we have this being a double. Make sure this is a float. Okay, fine. Let's make a cosine as well. And then we're going to say this is going to be cosine and the sine. So this will now move in a circle depending on the angle. A circle that moves around the 0.0 point and has a radius 1. So we're going to want to change that, but let's just see what's going on. Okay, so we suddenly have changes in the light. You can see on the map here as well, the light suddenly started having an effect. It didn't before because it was so low that none of the things we view from above were lit. But now suddenly it's a bit higher, so things are lit from above. So you can see there are changes happening here. Something is happening with the light. Not interesting enough though, so let's figure out exactly where the center between them is. So let's say, I don't know, something like 15 plus the cosine. So now we're changing the center. Okay, is it between them now? Now it's here in between, but it's somewhere off to the center here, so it's probably, can take the z and put it to minus 15 plus the sine. Now I can almost see nothing here. Where is everything being lit from? Wondering if this yellow one is being lit from inside. So we go inside it. Alright, minus 15 was a bit too far. Let's make it minus 5. Let's see if we can put this right between them. Okay, so they're sort of being lit from these sides. Or right now it's somewhere inside this pyramid here. We're moving around it. That's cool. Let's make the radius bigger now. So this set the center by multiplying or scaling the cosine and sine by something. Could actually just take this and, oh no, let's scale it in here. Times 10. Sine times 10 as well. Let's see what happens now. Sort of going back and forth. Am I using sine and sine, or am I using cosine and sine? Ah, of course, cosine. That'll make a difference to make it actually go in a circle. So there. Now I can actually see on the map here, it's moving kind of around here. The x coordinates are a bit too far as well. I'm not even sure what's x and what's z here. This whole pyramid structure is very confusing. Okay, now it's moving in circles here inside it. And if we make the radius even bigger, we can probably make it actually look like it's moving around them on the outside. Okay, so this is moving kind of fast now. You can see because these are all flat spots here, or flat surfaces, it's just kind of, because it's so far away now, we don't really see how it's gradiently moving in circles. So we might actually, before we do the whole pyramid, we might add something similar to this, except add a sphere maybe. So yeah, add some material diffuse here, let's have it some other color, 0.3, 0.7, I don't know, some color. Let's make it sphere graphic, solid sphere, like so. And we don't want this translation, instead we want, let's just put it right in the center. Let's put it where the light is, or where the circle that the light is moving around is centered. And we can actually see where that is. Let's see what happens now. Okay, there's a sphere there. You can see on the sphere, especially if we move above it, you can see how the light is moving in circles around it. Very nice and smooth. So the light is moving around this. This is a ridiculously low detail sphere. Let's fix that a little bit. Sphere graphic. This is ridiculous. 24, 24 or something like that. You can see it here as well. Let's go in a bit closer. Okay, here, so the light is moving around. So we have different colors on the materials. And now, in order to really disco this up, we can go ahead and add the sign function to the colors as well. So go into the game class, go in here, let's just add that to the diffuse on the sphere. So let's make these again, and let's change the angle a little bit. Angle divided by 2. Let's have a more weird number here. And cosine of the angle times 1 point something. And let's just set these values here to the red and blue. Set the green value fairly low. So sine can be a negative number as well. So either we can do a max here, or we can do an absolute. So math dot absolute of this, just to make sure we don't get minus values in the colors. You can experiment with that, see how that looks, but I'm not interested right now. And let's just see what happens. to do. Not to the material diffuse, we're going to do this to the light diffuse. The material we just want it to be unchanged. So let's actually, it'll look the same now if I simply go ahead here and say I'm going to make this a completely white object, and then I'm going to send this light onto it. And then we can see how the value of the light is changing at the same time as it's spinning. And finally, okay, we have such a strong color here, that's why I didn't see it more purple. Green was always. Okay, so now we can actually see how it affects the pyramids as well. Suddenly the green value is really low, so we're just getting purple parts, so the yellow sometimes completely disappears. So just go crazy with this and see what you can do. These colors, 0.3 is a bit low, it's 0. Well, it doesn't matter. What I was wondering here, we're moving the light, we're changing the color of the light, and then of course we can change the material as well. So let's make sure this material doesn't have much red value. Well, let's have full green value and then sort of high blue value. So the material stands still, but the light diffuse is changing. And of course you can do either one. You can have one object in your scene with changing materials, or you can have the lights changing. In the end, you kind of have to make sure that you're not making everything too complicated for yourself to understand. Like it is now, you know that it won't matter for how the sphere looks, whether I'm changing the light or its material. If I always have a white light and change the material, it looks the same as if I always have a white material and change the light. However, if we look at the pyramids, obviously since the light is affecting them as well, if I were to swap it around again and say, now I'm going to have this the material, but the light stays fixed, then suddenly only the sphere is being affected by these color changes. So the color changes are within the sphere, only that is being affected, while the pyramids are being lit up. By a constant light. So they're still just yellow and blue, except not as yellow and as blue as they were before, because it's not always a white light lighting them up. But this disco color change is only affecting the sphere right now, whereas if I change it back, it's now affecting the entire thing and everything's going purple and weird. So that's it for now. The main thing here is we moved all the stuff to the shader. Now I can manipulate that. We set the light diffuse, we set the material diffuse, and we do that through the shader. We do that at the same spots as we were changing the color before. Otherwise everything's unchanged. Now, however, when we're setting the matrices, we're doing that through the shader. The only thing we allow to be sent out of the shader is the vertex array position and the normal array position for the shapes themselves to manipulate that. But you can just decide exactly how you're going to have everything structured and in which direction everything flows. But I'd recommend flowing as much data towards the shader rather than taking data from the shader and distributing it around your program. So we're trying to do that where we can. And then of course we have the vertex shader itself using these values, calculating with them like this, and the shader itself getting the locations for these variables and setting up functions in order to affect these particular variables. And then just add on to this look at specularity and look at all kinds of things, but you have all the math. So now we've taken the math for the diffuse lighting and we put that in there. There's no problem now to take the math for the specular lighting as well. What you need for the specular lighting is you need a variable for the camera position as well. Since the view matrix, you can't really pull the camera position very easily out of it. It's just simpler to send the position in there. But once you have the camera position in there as well, just like the light position, and have it inside your Vertex Shader as well, the camera position, you can just set up the same kind of calculation as we do here for Lambert. Set that up for Fong. Make sure you have the shininess there as well, and you'll have the specularity. Look at that in class soon enough.